Hello, my name is Mukesh Kumar. I'm a marketing director with the Embedded Processors Group here at Texas Instruments, and I'm here today to talk to you about DSP technology for video processing. Before we get started, I wanted to highlight a few data points, some research done by independent agencies, which suggests how the growth of video traffic is basically being driven by mobile technology. And I have put up some research done by independent agencies here just to highlight the point. By 2012, there will be 975 million mobile users, web users. YouTube accounts for 17% of mobile data bandwidth today, and that's all video. By 2015, video will probably make up to 68% of all mobile traffic in US. And to add to all of this, connected TV shipments, that is TVs with internet connectivity, is already growing and will exceed 138 million units annually by 2015. Overall, mobile data is set to grow 40-fold over the next 5 years. And streaming video content as a percentage of all traffic will be about 20% by 2013. Essentially, what this is telling you is there is a lot of video which needs to be processed. Video processing infrastructure actually spans across different phases of video life. It starts from content creation. Video processing is required during distribution, during post-production, for monitoring, formatting, you name it. So video processing per se is required in many different end applications. It can be an encoder, it can be live production equipment, transcoders, translators. Even surveillance and analytics is very heavily dependent on video processing. Now, there are certain industry trends that we should all note. First, the innovation in video technology is not abating. There are standard video codecs which have been in existence for a long time now, MPEG-2 for example, but there are lots of new technologies being introduced like HEVC, that is H.265. 4K resolution is now becoming a reality. Adobe has HTTP dynamic streaming, and the list just keeps going on. But this is the video encoding and decoding part. The type and number of display units is also increasing tremendously. You can have a small smartphone in your hand, and you can have a very large high-definition TV in your home. And the video infrastructure has to cater to both. And all this has to be done, but the need to drive better economics is becoming more and more important. Just to give you an example, a comparison with audio processing. Today, you can do 8,000 to up to 14,000 voice channels per ATCA card based on a DSP. But if you look at the DSP channel densities, you can barely do 100 video channels at D1 resolution. So essentially, that channel density definitely has to go up. And all this is basically has to be done while reducing power, while reducing system cost, and increasing channel density. And all this while meeting the time to market requirements for new technologies as they come about. Just to look at the new technology life cycle, this is a standard technology life cycle for any product, and it basically says that in the introductory stage, you have different concerns from growth stage or maturity stage. In introductory stage, it's all about fast time to market. In the growth stage, you are talking a lot more about getting the right channel density, meeting the price requirements, having the scalability to design different types of products. When you get into the mature stage, it's all about price pressure. Now, if we look at all the codec and the video processing technology world, you see MPEG-2, which is probably in the decline stage now. You have codecs like AC3, H.264, which are more mature to declining stage. You have AAC, which is just getting out of the growth stage into the maturity stage. And then on the left, you see all these new codecs and systems coming into picture, VP8, H.265, SVC, HTTP streaming, which are all basically in their nascent stages today. What does this mean? In many cases, there is a need to support all or varying subsets, and only a flexible system design can make this possible. And that it can do by meeting time to market needs for the new technology, meeting the channel per dollar requirement, channel density and scalability needs of the growth stage, and meeting strong price pressure requirement of mature stage. At TI, we offer two distinct architectures. One is a pure software-based multi-core DSP. An example of that would be TMS 320C6678, or an SOC-based architecture like DM8169. And both of these architectures have their advantages. On the multi-core side, you can get true flexibility because the entire software, entire codec, everything is fully software implementation. That gives you a lot of flexibility. It enables customers to differentiate because everybody can implement their own systems in a different way. Scalability, that is being able to design systems for very high dense multi-core processor-based systems, or to achieve peak performance, or to low channel count small systems. That scalability is offered by a pure software programmable DSP. And not to mention, or we should not forget that it definitely provides the longevity and future proofing in terms of designing and hardware and being able to implement new codec technologies or video processing technologies on the same hardware, which is not necessarily possible in an SoC based system. However, the SoC architecture has its own advantages. It gives you a high channel density, and that's primarily because of the hardware acceleration. You get a lot of system integration because of the specialized video peripherals that you can get on the chip itself, and that basically helps you cost optimize your integrated system. And SoC reduces the need for specialized video algorithm development because most of it is already done in the hardware accelerator, which basically means it lowers your time to market. Now let's quickly look at some features of a software programmable multi-core DSP, which would make it more suitable for video processing. And I'm using 6678 as an example here. It gives you very high performance, 320 gigamax, 160 gigaflops at very low powers. It gives you the scalability that you need, ability to go from a single core version all the way to 8 core. For video processing, you need very fast external memory, something like a DDR3 1600 megahertz. You need large addressable memory space. And on top of that, to get the requisite performance, you need large on-chip memory. For example, this particular device has 8 megabytes of on-chip RAM. And all this gives you the ability to handle large image data. Now, the next problem is how do you get data in and out of the device? High bandwidth interfaces, things like serial rapid I/O, PCI Express, gigabit Ethernet, they all give you different types of connectivity. For example, backplane communication, TCP/IP network connectivity, or SoC or server connectivity through PCI Express. Now, oftentimes you would find that in a system you would have a DSP, but you would also have a need for an FPGA, and there needs to be a very thick pipe between the FPGA and a DSP to exchange a lot of data. Hyperlink is one such interface on 6678, which gives you up to 50 gigabits per second serial link to FPGAs or possibly to other DSPs like another 6678. Now, to get the requisite performance entitlement from a multi-core DSP, you also need things like hardware-assisted on-chip communication. Or for TCP/IP, you need network coprocessor and security accelerator. And then the overall system architecture should actually allow you to get the performance. TeraNet, this high-speed switching fabric, is just one example of that. Now let's look at what does an SoC architecture like DM8169 bring in. Here is a block diagram of that device. It has an ARM, it has a DSP, and it has a bunch of accelerators. You have accelerators for taking care of the capture and display functionality. You have accelerator for video encode and decode functionality. You have a DSP which can handle audio and video processing outside of the encode and decode functionality. And then you have an ARM system which does all the control processing. And to support all of this, you have many different interfaces which are all shown at the bottom. But the reality is, for designs where you need both flexibility and density, And that's to take care of both the old technology as well as the new ones. The solution probably is a combination of both an SoC and a fully programmable DSP. And here is just an example of a board where you have DM8169 connected to a 6678 for the software programmability aspect of this. But a DSP is not enough. You generally, if you're a video developer, you would need multiple types of hardware depending on what end application or applications you may be developing. And what I have highlighted here is how there are various form factor cards like AMC form factor, half-length PCI Express consuming 54 watts, having 4 of the 6678 devices. You have a full-length PCI Express card which consumes 110 watts but has 8 6678 devices. And then if you want even more performance, here is an ATCA blade consuming 350 watts but has 20 6678 multi-core processors. And just to remind, each one of these 6678 processors brings 320 gigamax and 160 gigaflops of performance. So that's a lot of performance for the power that you see for those boards. Again, hardware is not sufficient. You need the requisite software which can help you develop this video solution that you want to. And what we have done at TI is basically give out or come up with a software solution called Multi-Core Software Development Kit. That's actually a combination or a collection of multi-core aware software development tools, real-time OSs, device drivers, hardware abstraction layer software, libraries, and so on and so forth. And based on that multi-core software development kit, we have built a audio video processing framework. So this entitlement software along with the tools and a demo application, in this case I'm just highlighting one demo we did on a single 6678. We showed translating of 70 channels of QSIF H.264 video at 30 frames per second. All this software can help you get started quickly and not have to design systems from scratch. But again, this is not sufficient. You need hardware, you need enabling software, but then you need a lot of software which TI or a processor company will probably not develop, and that's where a partner network is a tremendous help. We have partners like PathPartner, Kuth IT, ETM, who are more on the video processing side. We have Polycore, Critical Blue, which are more on multi-core software development tool side. And then you have eInfochips, Z3, and Advantech, who are all our hardware partners. And in fact, Advantech developed those PCI Express cards and the AMC form factor card that you see on top. I would like to end by summarizing what I've been saying so far. And that basically is more and more video is being created, stored, and consumed. More and more disruptive new technologies are constantly being introduced. And now, to support both of these, video processing hardware needs to support both technical and business demands. And we think a combination of pure DSPs and SoCs has clear advantages in terms of lowering cost, lowering system power, giving you the requisite performance, giving you the scalability and flexibility that is required, and overall reduce the time to market for video systems. It takes, however, more than just a DSP to develop an efficient system based on DSP. As we spoke in the last slide, there is a need for different hardware, there is a need for many software pieces which can come from many different companies. And put together, that can enable someone to develop a good video system. And TI has a rich portfolio of DSPs and SoCs suitable for video processing along with the enabling technologies. With that said, I want to thank you for listening to me and giving me your time.